Hello everyone, my name is Ori and today I will talk about the problem of multi-robot dynamic swarm disablement. In this work, we have defined and applied algorithmic problem that belongs to the multi-robot world motivated by agricultural application of pest disablement. In the dynamic swarm disablement problem, we are given k robots and n harmful swarm agents. The robots have the ability to disable locust agents within a certain range of D. The swarm passes through a given area, and each swarm agent makes damage unit each step before it is disabled. The movement direction of the swarm, motivated by real locust swarms, is known to be forward. We discuss here only deterministic constant direction, but in further work we consider a distribution of directions too. Given these settings, we would like to disable the swarm agents quick in the manner of minimizing the damage. To summarize, our goal is to find the robot's movement that minimizes the accumulated damage or lifetime of the swarm agents. We show that the general problem is hard, so we do not expect to find the global optimal solution. Instead, we find the best solutions among a subset we call blocking line solutions. Although the additional information about the agent's movement does not change the essence of the problem, it is clear we can do better than conducting separate one-on-one chasings. The common direction of the agents let us make decisions that are good in a macro view and not only local greedy decisions. The use of blocking lines instead of conducting chases has many advantages. Among them, first, scalability and handling massive swarms. Second, it is suited for inferior, few, and slow robots. Third, it has a fast completion time. And finally, it is more suited to handle stochastic agents. We first separate the scenarios into two types, full blockage case and partial blockage case. In full blockage, there are enough robots to cover the range of the swarm agents and perform a full blocking line. If it holds, the problem is relaxed and turns to be one-dimensional in some sense. For the full blockage case, we presented three algorithms: static line, traveling line, and a variant named separate traveling. In the second type, the partial blockage case, the robots cannot fully cover the terrain and they need to move also in a patrol style in order to block efficiently. For the partial blockage case, we presented an algorithm named static line lag and additional two variants, additive static lag and separate static lag. In static line, the robots form a line and stay in place. The goal of static line is to find the optimal line and assignment for the robots that minimizes the accumulated damage. The algorithm is inferior relative to other blocking line algorithms, but still it outperforms benchmark algorithms in some cases. In traveling line, we aim to find the optimal full line and its vertical movements, minimizing the accumulated damage. This is done by a dynamic programming solution for the one-dimensional traveling repairment problem. In separate traveling, we separate the space into vertical sections that a single robot can cover. For each section, we apply a traveling line solution. It cannot be worse than traveling line since it can find in particular the solution of traveling line 2, while its actual computation time is significantly better. The first algorithm for partial blockage is static line lag, which is a static line when we have a lack of robots. We find the optimal line and the horizontal movements of the robots along it, minimizing the accumulated damage. Based on a recent work of multi-robot patrolling, we formulate the disablement options of the robots as a graph and apply a max flow min cost mechanism on it. A variant of the previous algorithm is additive static lag, in which we apply static line lag on upcoming waves of agents. Practically, this algorithm achieves relatively good results, even relative to the original static line lag. Another version is separate static lag, in which we apply static line lag in separate packets, similar to the idea of separate traveling. The performance of this algorithm is relatively good, but its computation time is greater than the previous. We have compared the blocking line solutions together with other solutions in the literature we call the assignment base as baseline. The first assignment-based algorithm is iterative assignment, in which we reapply the Hungarian assignment algorithm in iterations. The second algorithm, which is k-means assignment, uses additional clustering phase before applying the assignment. We present you some highlights of the results. When examining the swarm size and the speed of the robots, we can see the blocking lines get better as the robots become inferior. Among the blocking lines, the separate traveling, which is the green line here, works great in a reasonable computation time. For the partial blockage case, the blocking lines also become relatively better as the robots are inferior. In particular, the proven blue line static line lag works great, but practically the heuristic additive static lag and separate static lag can perform good as well. Speaking about the computation time of the algorithms, the full blockage traveling line and the partial blockage static line lag perform well, but become infeasible very early. Instead, we can have the separate traveling and the separate static lag that perform well in a much reasonable computation times. And now is the time to sum up. We first defined the DSD multi-orbit problem and found it to be NP-hard. Although the hardness of the problem, we have suggested methods to handle the problem based on an intuitive idea of blocking lines. We've tested the algorithms empirically and they're shown to perform very well. There are many directions in which the research can continue. First, extending the problem and its solutions to handle agents with stochastic movement. Second, using more solvable variants like TSP on parallel lines, for example, to formulate additional solutions. Third, the approach of reinforcement learning, in which the robots learn by trial and error, could be efficient and worth testing too. And that's it. Thanks for watching and feel free to contact us.